Some compounds have more than one stereogenic center, or chiral carbon. Here, this example, 2-bromo-3-chlorobutane, has 2 stereogenic centers. This one right here has a hydrogen, a bromine group, a methyl group, and the rest of the molecule. And this carbon has a hydrogen, a chlorine, a methyl, and the rest of the molecule. And so both of those are stereogenic centers. Each of them can be R or S. And so then you have 4 different possibilities. So you could have both of them be R, you could have both of them be S, you could have the second carbon be R and the third carbon S, or the second carbon S and the third carbon R. And so you can imagine as you increase the number of stereogenic centers, the number of possible isomers just explodes. If we look at these two, these are the 4 different isomers of that molecule we just looked at. And here they are drawn with wedges. Let's draw the Fischer projection for these isomers. They're drawn up here in a way that makes drawing the Fischer projection easy because the horizontal lines need to be coming out at you, and they are in this situation. So we go like that. We have 2 stereogenic centers. We've got I'm sorry, that's not an H. We've got chlorine there, and hydrogen, and bromine, and hydrogen, and a CH3 at the bottom, and a CH3 at the top. And this is the next one over. And it also has those at the top and bottom. So this is one where both carbons are R, and this is one where they're both S. So these two are mirror images of each other. They're enantiomers. Enantiomers are non-superimposable mirror images. And then the pair over here when we use the Fischer projections, it's much easier to draw things in a consistent manner so that it's easy to compare them. So in this one, the top carbon here is R. So the bromine's on the left and the hydrogen's on the right. And over here, this carbon is also R. It's got the same order of groups around it. We're keeping the methyl groups top and bottom just so that they're all looking similar. We're looking at this in the same way. So the methyl groups. And the mirror image of this one will have the H's over here and the halogens over here. So here, this one's R and S, and the mirror image is S and R. So there are 2 pairs of mirror images in enantiomers.
Can you figure out it the same way? Can you show us how to figure out the priority and stuff on these ones?
I can, yeah. Now, looking at each of these, the hydrogen is not in the vertical position. So we're going to need to move them around. Let's just do one of them, okay? Let's see. I'm just going to make a little space here, and I'm going to do this guy, and hopefully we'll be able to show how it matches up being S and R. So if I want to move this so that the hydrogen is in a vertical position, I need to move the other 3. Okay, I'm going to need more space even, because it's going to end up going sideways. So I want to put, let's put the hydrogen up. Yeah, no matter what I do, it's going to end up being weird. So we're going to move the hydrogen up. Let's just, Let's keep the bromine the same, just because. So if I keep the bromine the same, and I move the hydrogen up, then this methyl group comes down, and the rest of the molecule ends up being off to the left. So that's this part. This part moved over. Okay, so that's one of them. Now we need, this is, I would never make you do this. Here we want to, let's put the hydrogen also, we want to move this over here. Let's put the hydrogen up as well. So we're moving the hydrogen up, and if we keep, we have to keep one of these the same. We can't keep the methyl, we can't keep this the same because that has to move. We can't keep the chlorine group the same. Let's keep the CH3 group the same. So if we keep this one the same, and we're going to rotate them around, we're going to rotate the hydrogen up, the rest of the molecule goes to the right, and the chlorine comes out on the end. Now we can look at the configuration with the hydrogen being in the back. The bromine's number 1, and this part is number 2, and this is number 3, and so this one's going around to the left, that one's S. And what do you know, that one's S. And if we look at this one, hydrogen's in the back, chlorine's number 1, this group over here is number 2, and this is number 3, and so this one's going around to the right. Did that make any sense at all?
It's kind of difficult to understand how you flipped it.
It is hard to understand how you flip it. So when I flipped this, especially on one with 2 stereogenic centers, I want to put the hydrogen either up or down. I just arbitrarily decided up. And then you have to choose one of the other 3 groups to stay the same. And so I kept the bromine the same. I didn't move him. And so I moved this one up. The methyl skips the bromine and comes down, and then this guy comes over here. So the one that you're holding steady, that one is, you could think of it as being behind, and you're rotating the other 3. So on 2 dimensions, it looks like you're skipping that position. And then that one, that's even more confusing. That was a really hard question. Any other questions? I would not ask you to do something like that. That's just not very nice. This is a slide trying to explain what we're looking at when we're looking at this Fischer projection. So the Fischer projection is like you were looking down on the eclipsed conformation of this particular molecule. So this is showing that this chlorine is sticking out at us and this hydrogen is sticking out at us. If we're looking down on it, the hydrogen is coming up, the chlorine is coming up. This part and that part are basically going down. This one, this carbon, the bromine and hydrogen are sticking up. And looking down on this, those 2 are sticking up, and the methyl and the rest of the molecule are down. This one's down, this one's down. So this is a wedge, and this is dashed. This is dashed. Wedge, wedge, dashed. Looks like a skeleton with 2 bow ties. Okay, so that's what we're trying to look at when we look at the Fischer projection. Now, this is not the preferred configuration of this molecule. It's going to want to be staggered instead. But the staggered eclipse thing is just a rotation, and that happens, and so we're just choosing to look at it in the most convenient way. And you can imagine what fun they had trying to figure out all the sugars. Many of the sugars are hexoses, and they have 5. Take that back. I think they have 4 stereogenic centers on them. And the absolute configuration on each carbon is very, very significant because you switch one and you've got a different sugar. And so there's this huge family of carbohydrates that are all so incredibly closely related, and the stereochemistry is just very, very important for them. And the Fischer projections are just really a lifesaver in looking at the sugar molecules. So diastereomers are stereoisomers that are not mirror images of each other. So let's go back here real quick. These two are mirror images of each other. These two are mirror images of each other. But this one and this one are not mirror images. Do you see that? This one and this one. These two are not mirror images of each other. But they are stereoisomers. But they're stereoisomers that are not mirror images. So these are 4 different stereoisomers of one compound. All of the atoms are connected in the same way. The difference is the stereochemistry around these carbons. This one and this one are mirror images. These two are mirror images. If this one looks in the mirror, he sees that. But this one is not a mirror image of that, because they have the same configuration around one carbon, but a different configuration around the other carbon. Do you see that? So those are not enantiomers. They're diastereomers. Do you love all these words that they have for these different? It's very confusing. So enantiomers are mirror images. Diastereomers are stereoisomers, but they are not mirror images of one another. So diastereomers can differ in all of their properties. So they could differ in their density, they could differ in their melting and boiling points. Enantiomers, because they are mirror images, they only differ in properties that are chiral. Their interaction with another chiral molecule, their interaction with light. But diastereomers can differ in more ways. So how do you expect the specific rotations of 2R3R and 2S3S forms of 2-bromo-3-chlorobutane to be related? This is that same molecule that we've been looking at in multiple slides. So the ones we're looking at here, one of the carbons, the first carbon is R, the second carbon is R, and in the other form, both of them are S. Are those going to be mirror images? This is one molecule. Here, we actually have pictures of them. So both of them R is this guy, and both of them S is this one. Are they mirror images? Yeah, they are. So those are mirror images. That means they're enantiomers. So when we think about how do we expect the specific rotation, that's the rotation of light, how do we expect the rotation of light to be related between those two? Opposite. They should rotate an equal number of degrees, but in the opposite direction, right? Because they're mirror images of each other. What about 2R3R and 2S3R? Are these guys mirror images? No, they're not mirror images. We really can't say anything then about the specific rotation of the light for these two.
They could even have different boiling points.
They could have different number of degrees. They could end up both going to the right or both going to the left. They could be one right, one left. This one might be minus 3.33 degrees. Oops. This one might be, maybe that one's minus 3 degrees. This one might be minus 6 degrees. You can't predict just by looking at it. When they are mirror images like the first two, you know that the number of degrees is the same, the direction is opposite. The number of stereoisomers, the more stereogenic centers you have, the more possibilities for stereoisomers. And there's this little formula which relates to statistics, basically, 2 to the n, where n is the number of stereogenic centers. Because each of those centers has 2 possibilities, and so we get 2 to the n. That's the maximum number of stereoisomers. Sometimes there's less than that, but that's the maximum. So if you get, 6 stereogenic centers, you've got 2 raised to the 6th power. I'm not even sure what that is, but it's a big number.